Hello everyone, good morning. Welcome back to my channel Learn Tech with Kiran. In previous session, we generate grammar for only two symbols. But in today's session, we discuss problem with a three symbol or a terminal we can say. While we dealing with three symbol or a terminal, we need to deal with quite differently. Appearance of a one symbol count may depend on a other. Here you can see your J count or a one count is depend on your I and K count. Okay. For more understanding, let's start the session with problem statement. Consider write context free grammar for the following language where your language is 0 raised to the power I, 1 raised to the power j, 0 raised to the power k, where your j is greater than I plus k. Okay. So first let's understood how can this problem solve or how can we generate a context free grammar for a given language. Now let's break down the language so we can easily generate context free production rule. Okay. Let's consider this language is a three part. For example, 0, 1 and 0, correct? And we have to generate production rules for each one of. Okay. Now let's focus on language. Now as per problem statement, your j should be greater than I plus k. Now according to this, let's generate a language first so we can understand the pattern of a language which is generated by this problem statement. Okay. Now j is greater than I plus k. Okay. So if your I is equals to 0 and k is equals to 0, which means your j is supposed to be greater than or equals to 1 because your I and k is not there. So that's why your 0 is not appear over here, but your j is greater than or equals to 1. Okay. So that's why your string is 1. Then another condition is I is equals to 1 and k is equals to 0. So in this condition your j must be greater than 1. Okay. So I plus k value is nothing but 1. So that's why your j must be greater than or 1. Okay. So that's why here you can see your appearance of 1 is over 1 1. Okay. Next one is I is equals to 0 and k is equals to 1. As we design the grammar, as we design a string for a I is equals to 1 and k is equals to 0, similarly you are supposed to design this string for a this one. Accordingly, following strings are generated. So let's look on it. Here your I is equals to, here your I is equals to 1, k is equals to 1. So your appearance of 0 is 1 time and your 1 is must be appear than greater than 2 times. Okay. So that's why I am writing over here 3 times 1. Okay. Then here maybe greater than 2, it means maybe it 3, maybe it may be 4. Okay. So that's why I am taking a 2 string over here. One with a 3 1 and second one with a 4 appearance of 1. Okay. Then accordingly following grammars also generated for. Now this is our string set designed as per our given problem. Okay. Now, as per generated string, we can simplify this as follows. As our j is greater than I plus k. Okay, it means if your I is incremented, then your j must be increment. Okay, same for your k value. Correct. That's why we attach appearance of 1 which is depend on I and k. Okay, will combine with I and k. Okay, so here you can see I combine this I combine this one with I value, then another one with a k value. Okay, so when your I incremented for a 0, the same time your j incremented. Okay, so it means we combine our j in I m. Okay, so now why this m over here? When 0 value is incremented for I, same time your 1 will be incremented as it have to be increment. Okay. Now similarly when your k is increment, okay, the same time your 1 value also appear over here. It means when your 0 appears, at the same time your 1 appear with a k value, and when your 0 appear with a I value, the same time your 1 will be appear over here with a I value. Okay. Now there is a one more condition. It's supposed to be greater than, okay, not equals to. If I am only writing 0 raised to the power I, 1 raised to the power I and 1 raised to the power k and 0 raised to the power k, it means it increment equally. Okay, So we have to generate a greater value. So that's why I am giving over here 1 with m value, which is another variable. Okay. Now for implementing CFG for this problem statement, it may be a complicated. Okay. So simply we break down this statement into 3, which is nothing but L1 is a part where we incremented a I value. Then 1 with a m value is differentiate in another one, and third part is related to your k increment. Okay, so simply we break down this, and now we generate a grammar for this 3, and then after we concatenate it. Okay, I hope you understand. Let's design a context free grammar for this equations. Now L1 is nothing but your 0 raised to the power I and 1 raised to the power I. Okay, so it may be repetitively generated, correct, because we needed 0 multiple time or a 1 multiple time. That's why what we have to create, we need 0 1, but we need 0 and 1, but in some of the cases the repetition of this appearance may be over there. Okay, so simply what you can write over here, a defined variable for this value. Okay, now I need 0 and 1, but sometimes I need repetitively, correct? For a repeatedly appearance, I add this a over here. It means when I want more appearance of this equation or this value, I am replacing this a again with this same expression. Okay, but at a time of efficient appearance of a 0 and 1, I have to terminate this, correct? So that's why I substitute this a with a epsilon, which is nothing but a empty. Okay, so this is how I was generated the grammar for a this specific string. Now let's generate a another grammar for another one, which is nothing but a 1 raised to the power m. So your L2 is nothing but a 1 raised to the power m. It means one appearance may be repetitive. Okay, so that's why what I generate, b tends to 1 I have to generate, correct? Then for a repetition I add a b. Okay, then your appearance of 1 will be generated by this b value. Okay, when you want to terminate, you replace this b with a 1. Okay, so there is a no epsilon. Okay, because you must generate your j value is a greater than I plus k. If I replace this one with a epsilon, it means at the initial level, if I substitute this b with a epsilon, it means your j value is equal to the I plus k value. Okay, so for this condition I am adding 1 over here. Now your third language is 1 raised to the power k and 0 raised to the power k. Look at here, we generate for a 0 raised to the power 1 and 1 raised to the power 1, correct? The same logic we implemented for a third one. Okay, so here you can see your your L3 is equal to 1 raised to the power k and 0 raised to the power k, correct? I use c variable over here for this implementation. Okay, now I want 1 and 0 appearance, so that's why I mentioned 1 and 0. For repetition or a recursiveness, I use c over here. Okay, so why I am using this c over here within between 2 1 and 0, because you can see over here your language must be generated 0 followed by 1, and this 1 is followed by 0. Okay, if I write this c afterward of this, okay, after a 0, it means what, 1 0 may be substitute multiple time. Okay, so your string may be disturbed, or the equation we have to generate it as per our problem statement may affect. Okay, so that's why appearance of a and appearance of c is between your both of the symbol. Okay, so whenever you generate a string, it in the form of 0 after 1 and after all zeros. Okay, I hope you understand this implementation. Now we have to concatenate this. Okay, because it is a part of one language, so that's why we have to concatenate. Now at the initial point or a starting point, we have to use all these three, correct? So that's why I'm writing over here a, b and c. After this we have to write this implemented grammar as a part of our context free grammar. So this is your generated production rule for your given language. Okay, I hope you understand this. Now let's discuss validations. Now validations is nothing but the production rule we already defined whether it is able to generate all the language or all the string set which is generated by our problem statement or not. So these are production rules we generated, correct? Now let's discuss with a one. Okay, so here you can see I have to generate a string one. Okay, so that's why I'm substituting or initiating with a starting symbol which is nothing but s. Okay, so here you can see I have to generate only one. So you have to check where it is from your production rule it is appearing a 1. So when you substitute your b with 1, you able to generate this string. Okay, if I substitute a for a 1, it means it came with a 0, and same 1 is also, and same 1 is over here, but it is came with a 0. So that's why I have to substitute my b with a 1. Okay, rather than this I have to substitute this c with a epsilon which is nothing but a empty string, as well as a with a empty string. Okay, so in this example I implemented a rightmost derivation first. Okay, that's why I'm substituting my rightmost variable c with a epsilon, then my b with a 1, and at the end here you can see I'm substituting my a with a epsilon which is nothing but your third expression. Okay, so for a substitution there is a each rule I mention over here. So you can see when I substituting c with epsilon, it means this is a seventh rule. When I'm substituting b with a 1, it means this is a fifth rule. Okay, so you can see over here, then I'm substituting a with a epsilon which is a third rule. Now second one is a 0 1 1. So basically I have to check where 0 and 1 is generated, or starting with 0 where it is generated. Now if 1 0, if c is substituted, okay, then 1 0 will be generated, but I want 0 and 1, so that's why I'm substituting a with 0 1. Okay, so here you can see a substituted by 0 a and 1. Now this part is completed, that's why I'm substituting this a with a epsilon in this case. Okay, then b and c as it is over here. Now I have to substitute b for a 1. Okay, so that's why I'm substituting b with 1 as per fifth rule. Okay, then after that I already generated my whole string, and now I am substituting my c with a epsilon. Lastly, this is a generated string. So this is how you have to substitute your production rules for your string generation. Okay. Now next one is 110. Similarly, I am implementing this 110 over here. Starting symbol is same, which is ABC. Now I have to generate 110. So 10 is generated with the help of C, but 1 is generated with the help of B. So that's why I'm going to firstly substitute A with a epsilon, then B and C over there. Now B is substituted by 1, okay, as per fifth rule. Then your C is substituted by 1, C and 0. Okay, so from this 1 and 0 is there. Okay, now here you can see 110, your string is already generated. So that's why you have to substitute your C with a epsilon. Okay. Similarly, these two more example from same string set I am implemented over here. Okay, these all strings are generated with the help of this production rule. So that's why these production rules are sufficient for implementing a problem statement. Okay, now we have to write a context-free grammar in the form of 4 tuple. Okay, so these are a 4 tuple which is a part of your context-free grammar, which is nothing but V, T, P and S. As per our given production, where your V is nothing but a S, A, B and C. These are some variable or non-terminal we use in a generation of context-free grammar or a production rule. Okay, then what is T over here? T is nothing but your terminal or a symbol. Okay, so 0 and 1, this symbol we use in our problem. Okay, now then production rule is mentioned as we used before or as we generate. Okay, then S is nothing but your starting symbol. As per our production rule, our starting symbol is S, so that's why I'm mentioning S over here as a starting symbol. Okay, I hope you understand this. That's it for today's session. I hope you found this video helpful. Don't forget to like this video, share with your friends and subscribe my channel. In next session, we will discuss one more important point in theory of computation. Thanks for watching.